In this example, we're going to revisit an old friend, namely the uniform line charge density that's running along the z-axis. For those of you that might recall, we solved this problem using Coulomb's law, and the whole point of this is we're going to use Gauss's law and recognize that and see that it's so much easier with Gauss's law. You might remember that when we were using Coulomb's law, we had to break out the integral table that we happened to fortunately have packed along with us onto the plane before we crashed onto that desert island and needed to solve that problem. In this episode, however, we are going to be equipped with Gauss's law, and there will be no integral tables involved at all. So again, where you have an infinite line charge, the charge density is rho L. It runs along the z-axis, and our goal is to find the E field, or an expression for the E field. So let's just go through it using the steps that we outlined when we were introducing the concepts. So the first step is the stop and think step, where we identify the coordinate system. Now remember that before, so as before, since it's running along the z-axis, we will use the cylindrical coordinate system since everything is radially symmetric about the z-axis. In that case, we are going to integrate across this closed surface here, this cylinder shape, the infamous toilet paper roll I had described before in prior examples. And in that case, the surface integral ds is going to be equal to the two directions are z, right? And then also phi, right? So let's just start with d phi, which is not in units of meters, so you got to multiply it by the radius, which is rho, and then dz. And this will be in the, so it's coming outwards, right? Or in the case of this three-dimensional situation, if your ds is these two dimensions, your unit vector for the surface is simply the remaining dimension, right? So it's going to be in the rho direction. And now we'll move on to the next step, which is where we set up Gauss's law. So in this case, we start by making the assumption that all the E fields, so again, charge are little arrow generators, right? So if we visualize a charge that's running along the z-axis, it will radially come out of the center about the z-axis. So it's going to be in all these directions that you see here, which is the rho hat direction. So your electric flux density is going to be equal to epsilon, and the only component is going to be a rho component in the rho hat direction. Now let's remember the situation where we said that for Gauss's law in integral form to work in finding the electric field, one of the key criteria is that it has to be independent of phi and z so that you can pull it out, right? You can see in this case it is, right? E rho, so it's an electric field, it changes, it's in the rho direction, and it probably only changes as a function of rho, right? If you shift it up and down or about the phi direction, you'll notice that that it's the same thing, right? So if they're equidistant, if all these points are equidistant from the z-axis, this person sees the same as this person at a different phi, or if you shift them up, this person also sees the same thing, right? So it's independent of phi and z, and that is a key criteria for this integral approach to work. So remember, if that is not the case, you're barking up the wrong tree, which is a very common mistake that happens, again, because the integral form of Gauss's law is often intuitively a little easier, so we try really hard to use it even during times when we can't sometimes. So let's set up the integral. So the integral of d dot ds is going to be equal to two integrals. Your electric flux density d is going to be epsilon E rho in the rho hat direction dot ds, which is this, also in the rho hat direction. So this dot product is going to be equal to 1. And then the remaining terms here is rho d phi dz. This runs from minus L over 2 to L over 2. If we're just going to let's just do it over for a length segment. And then we're going to rotate it from 0 to 2 pi. And some of you might say, well, why? I thought we were going to add it up from 0 to infinity. In this case, let's just keep it to L over 2 and minus L over 2, and we'll just say that if the problem doesn't work itself out, I have a feeling it might, but if it doesn't work itself out, you can then take the limit to go to infinity at a later time. Okay, next step is, so this gives us the left-hand side of Gauss's law. Now step 3 is to set up the right-hand side. So the total amount of charge enclosed when you're doing this closed form. Oh, another thing to point out is that since this is running up and down this direction, there are no fields going in the plus or minus z direction, right? So we don't have to worry about the top and bottom of this cylinder. Now the total charge enclosed for this length minus L over 2 to L over 2 is going to be equal to rho L, so it's a line charge density, dz. And we're going to also keep it equivalent to that cylinder there. We're going to integrate it from minus L over 2 to L over 2. Since it's a constant line charge density, this is just going to give you rho L z evaluated from minus L over 2 to L over 2, which is going to be equal to L rho L. And then next up, we just connect the left side and the right side of Gauss's law in integral form together. So we now have integral from 0 to 2 pi minus L over 2 to L over 2 of epsilon e rho d phi dz is going to be equal to L rho L. Now remember, this is where that magic happens, where we say this has to be independent of phi and z, right? Since it is, we can now pull it out. So we have epsilon e rho integral d phi 0 to 2 pi and integral dz from minus L over 2 to L over 2. And this quantity is going to be 2 pi. This quantity is going to be equal to L. And we'll keep the right side of the equation the same for now. We're going to clean it up a bit. So you're going to have now 2 pi L epsilon rho e rho is going to be equal to L rho L. And now that works out. So clean it up and solve for e rho. You're going to have e rho is going to be equal to rho L over 2 pi epsilon naught rho, which means that your E field is going to be equal to rho L over 2 pi epsilon naught rho in the rho hat direction. And I do realize just now that I was kind of sloppy and inconsistent with the case of my rho here. So I'll just clean that up really quick. And you'll see that this is the same result that we had when we were using Coulomb's law, except we need the help of an integral table. In this case, not so much, but it's also a good example to highlight why Gauss's law can make your life easier a lot of times when compared to Coulomb's law, but separately also highlight the key criteria to make Gauss's law in integral form work. So to recap, half the battle is identifying the correct coordinate system and defining your ds. But secondly, the other main test that you have to make sure checks out before you dive too far into it is that you can write a plausible electric field expression and find that it is independent of these two variables that you're integrating against. Because the key piece of the magic is that you pull it out of the integral, which enables you to then solve for the electric field and move everything to the other side. If you can't pull it out of the integral, then it's a lot harder to solve for it, and you might need to use a different tool. But otherwise, you arrive at the solution with relatively simple integrals, and life is much better because you know more now.